Welcome everyone to our explainer for subchapter 14.6. We're diving straight into some absolutely essential revision on network protocols today. If you've ever felt like the inner workings of the internet are just some kind of secret, totally impenetrable language, well, you're absolutely right. But don't worry, because today we are going to crack that code together. Before we get bogged down in the definitions, think about this for a second. Have you ever wondered how a video stream decides to prioritize speed? Like, why does it sometimes drop a few frames instead of pausing to perfectly buffer every single pixel? Why doesn't it just act like a standard file download that demands every single piece of data be perfectly in place? Well, the answer comes entirely down to the specific rules, the protocols, running constantly behind the scenes. Here's our roadmap for today's session. We'll kick things off by defining what a protocol actually is, then we'll compare TCP and UDP. After that, we'll hit the key network protocols you need for the exam, dive into addressing and packet switching, and finally, we'll wrap up with the protocol stacks. All right, let's jump right into section 1. What exactly is a protocol? The absolute crucial takeaway here is this specific exam definition. A network protocol is simply an agreed set of rules and conventions. That is literally it. Without devices using the exact same set of protocols, they can't identify themselves, they can't package data, and they definitely cannot communicate. It'd be like them trying to speak completely different languages. Now, there's a really fascinating contrast here when we talk about reliability. In networking, unreliable doesn't actually mean broken. Reliable protocols check for delivery. They basically want a receipt, which is absolutely perfect for critical data like your banking password. Unreliable protocols, on the other hand, like the video streaming we just mentioned, choose speed over error checking. They don't wait around for delivery notifications. They just keep that data flowing as fast as possible. Moving right along to section 2, let's compare the two absolute heavyweights of the internet, TCP and UDP. You are definitely going to want to know the differences outlined in this comparison chart for your exam. If you think about sending goods across the world, TCP is the meticulous packager. It's connection-oriented, meaning it sets up a formal handshake before sending anything, and it demands a signature upon delivery. If a data packet gets lost, it says, hey, send that again. UDP, though, totally connectionless. It just throws your package onto a ridiculously fast train and hopes for the best. There's no error checking, no handshakes, just pure, unadulterated speed. Okay, let's jump straight into section 3 and rapid fire through the key network protocols. Here is a highly structured breakdown of your absolute exam must-knows. Pay super close attention to the security differences here. HTTP handles your standard web traffic, but HTTPS adds a secure layer of SSL or TLS. You also need to know FTP for transferring files, using either active or passive modes, and RP, which is like a directory service that finds a device's physical MAC address from its IP address. Oh, and for remote access, remember that Telnet grants access with practically zero security, whereas SSH uses encryption to keep your remote commands entirely private. Make sure you don't mix those up. Also, watch out for this classic exam trap when it comes to retrieving your emails. Both of these are used for getting your mail, but IMAP is the go-to for modern users because it keeps your mails safely on the server, meaning it syncs perfectly across your phone, tablet, and laptop. POP3 is totally old school. It literally deletes the email from the server the exact moment it's downloaded to a single device. Once it's downloaded, it's gone from the cloud. All right, shifting gears to section 4, let's look at addressing and packet switching. So, for devices to actually talk to each other, they need addresses. Your MAC address is like your device's permanent physical fingerprint. It's stamped right onto the hardware at the factory, and it never changes. The IP address, however, is its logical, temporary location on a network, kind of like your home's current mailing address. And, fun fact, we actually had to invent the massive 128-bit IPv6 system because, thanks to all our smartphones and smart appliances, we literally ran out of the older 32-bit IP4 addresses. Crazy, right? Now, how does all this data actually travel? Packet switching brilliantly handles the traffic. Instead of sending a massive video file all at once over a single dedicated line, the file is shattered into tiny, manageable pieces called packets. Each packet gets a header with its destination IP address and travels completely independently. One packet might bounce through servers in London, another through Paris, dodging digital traffic jams along the way, and then they all magically reassemble in the perfect order the second they reach your screen. Finally, we arrive at section 5, the protocol stacks. As a piece of data, let's say an email, moves down the network stack from the application layer to the physical wire, it gets wrapped in different headers at each step. It picks up a TCP header to ensure reliability, an IP header so it knows where to route, and finally, an Ethernet frame header for the actual physical transport. It's exactly like putting a letter in an envelope, putting that envelope into a tracking pouch, and then tossing that pouch into a massive shipping crate. To really lock this concept in for the exam, let's use a fantastic visual metaphor. Think of the protocol stack like a literal layer cake. Data is pushed down through the layers on the sender side to be packaged up, and then on the receiver side, it is passed back up through the layers to be unwrapped, checked, and finally read by whatever software you're using. You absolutely must be able to compare the modern 4-layer TCP/IP model with the older but highly detailed 7-layer OSI model. Notice how the top 3 layers of the OSI model are totally squashed into just the application layer in TCP/IP. To really understand those OSI layers, think of a real-world corporate mailroom. The application layer is the CEO deciding to write a letter. Presentation translates it into the right language, session actually opens the door to the mailroom, transport decides if it needs a registered tracking number, network stamps on the postal address, data link hands it to the specific mail truck, and the physical layer? Well, that's the actual asphalt road the truck drives on. Okay, let's wrap this explainer up with a quick revision summary. Honestly, grab a quick screenshot of this summary right now to lock these core definitions into your memory. Remember the fundamental trade-off between TCP's bulletproof reliability and UDP's blazing speed. Keep in mind the permanent physical nature of MAC addresses versus the logical routing of IP addresses. And never forget how packet switching keeps the whole internet from just grinding to a complete halt. I'm going to leave you with these 3 exam-style questions to test how well you synthesize the material. Can you confidently answer all of them using what we just covered? Think about it. If you were building a brand new, wildly popular app today, would you choose the safe, steady handshake of TCP or the breakneck, risky speed of UDP to deliver your data to the world? Ponder that one for a bit. Good luck with your revision, and we'll catch you in the next explainer.